Hey guys, welcome to the channel. Today, in this session, we are going to learn master theorem. So, if you are following all the sessions on recurrences, I assume that at this point, you should be able to build a recurrence relation through a code, and you should be familiar with what are recurrences and recurrence relations and what is the purpose of creating a recurrence relation. So once you have a recurrence relation coming out of a code, the next step is to solve the recurrence so that you know what is the time complexity of that code or the asymptotic notation for that code. So in my initial sessions, I told that there are three ways to solve a recurrence. One is master method. Then we have substitution method. And the third is tree method. So in this session, we are going to look at how master theorem works and how it solves a recurrence. Master theorem is probably the easiest of all the methods because it works like a black box where you feed in the values as input and it returns the time complexity. The only assumption when you can use a master theorem is when all problems should be of the same size. What does that mean is, so let's say I have a recurrence which looks something like that. Okay. So if you see, and if you're following the previous sessions, the problem is divided in 3/4 and another part of the problem is divided into 1/4. So this means the problem sizes are not equal, or the problem is not being divided into equal parts. So we cannot use master theorem on this recurrence. Let's take another example. Now, if you see here, we are dividing our problem in half and in half. So the main problem is being subdivided into half and the subproblem sizes are equal. So we can use master theorem on this recurrence. Okay. So then if we generalize this, a general recurrence looks something like this. Okay, where the main problem is being divided into equal parts, right? And then we have a non-recursive code which is taking some time. Okay, so if we have a recurrence like this, then we say the recurrence time complexity would be log n if a is equal to b to the power d, and the recurrence time complexity would be if a is less than b to the power d, and n to the power log base b a if a is greater than b to the power d. And this is your master theorem. Now, how this master theorem is going to solve recurrences? Let's take a few examples so that it is more clear to you and you are able to grasp the whole concept. So let's take example 1, which is merge sort. So the merge sort recurrence looks like this. Okay, this means if we look at the above form of recurrence, we will say a is equal to 2, b is equal to 2, and d is equal to 1. This means a is b to the power d is equal to 2 and a is equal to 2. So what case we have? We have the first case where a is equal to b to the power d. And so the time complexity is n raised to the power d log n. And if we put the values, n, d is 1, n, which is O, n, and that's it. Isn't this the time complexity for a merge sort algorithm? Right? Okay. Let's take another example. binary search. The recurrence for binary search looks like this, right? This means A is equal to 1, B is equal to 2, and D is equal to 0. If we look at B raised to the power D, this will turn out to be 1 and A is equal to 1, which means A is equal to B to the power D, and this is case 1 again. So what does case 1 says? Case 1 says it's big O of n raised to the power D log n. So then and this is n raised to the power 0 log n, and this is O of log n, right? And that is the time complexity of binary search. Okay, let's take one more example, and this is our last example. Example 3, and that's Stresson's multiplication. Okay, and the recurrence looks like okay, this means A is equal to 7, B is equal to 2, and D is equal to 2. B raised to the power D is 2 raised to the power 2 equal to 4, and A is equal to 7. That means A is greater than B raised to the power D. What case this is? A is greater than B raised to the power D. This is case 3. Okay. So let's find out what the time complexity comes out. This will be n log base B A n log 2 7, and this is n raised to the power 2.81, and I think this is correct. Stresson's algorithm is subcubic time. So I hope this session on master theorem give you a good overview of how we can solve a recurrence to find the big O time complexity for that particular recurrence. I'm going to end this session here, and I will see you in our next session on solving the recurrences using tree method and substitution method. Thank you for watching and bye for now.